Good morning, everyone. Myself, Banerjee, and today I'm going to discuss our work, which is optimized misalignment correction from Cine MR slices using statistical shape model. Now, as you all know, that MRI is one of the gold standard imaging modalities for the acquisition of the soft tissues in different organs. However, unlike other organs, in cardiac MRI, the images are acquired over time in different acquisition planes. Now, biobank study, here you see that the images has been acquired in three different long axis planes and into a stack of short axis planes. If you look closely into the images, here you see this. These are the three long axis views, and these are the stack of short axis views. Now, in different clinical applications, one of the very important problem is the automated reconstruction of the both left ventricle and the right ventricle from the cinema slices. However, the biggest challenge during this reconstruction is the misalignment between the slices because these cinema slices are actually acquired sequentially but not simultaneously. And during the acquisition, the patients can move or they can take breathing or sometimes they can stop their breathing but at different time point into the respiratory cycle. So we can easily see that just by selecting three example cases. These are two long axis views and this is one short axis views, which we have oriented into the 3D system. So here if we see that the intersection between the four chamber long axis and the short axis plane, we see that along the intersection line, the myocardium here is very consistent. So this is perfectly resolving the problem. However, we see that here during the intersection between the three chamber long axis and the short axis plane, the myocardium is not consistent. They are completely discontinuous, and that means there is misalignment between the slices. We can also see that by selecting the intensity profile along the intersection line, and we see that along these two lines, the myocardial area is completely inconsistent. So if we try to do the 3D reconstruction of the meshes, we'll get erroneous reconstruction. So in order to provide the optimal biventricular mesh reconstruction from the cinema slices, we need to first perform the slice misalignment correction. However, in order to go to the misalignment correction step, first we need to identify where the heart surfaces are. That means where the heart epicardial and the endocardial surfaces are. Now, in order to obtain that, we have used a segmentation method developed by ONJY, where they used a fully convolutional neural network to automatically obtain the LV and RV cavity and the LV myocardium from the cinema slices. We have used that method to automatically obtain the LV and RV endocardium as well as the epicardial contours, and then we represented these contours into the 3D space and got a sparse 3D representation of the heart. Now, in order to perform the initial misalignment correction from these contours, we have done two steps. The first one uses an intensity-based method to optimally align the long axis and the short axis slices by optimizing over the intensity profiles. While the second method does essentially the same thing, but based on the contours. That means it tries to provide the optimal consistency between the long axis and the short axis slices based on the intersection of the endocardial and the epicardial contours. Now, using these two steps, we can get a good enough initial misalignment correction from the heart slices. And we can see that if just by simply selecting these two long axis planes. Now, if you see that in the misalignment slices, these are the short axis planes, and this is the total one. This is the long axis plane. Now, this red and this green are actually the endocardial and the epicardial contours intersection from the short axis planes. And you see that these points are very far from the actual endocardial and epicardial contours in the two-chamber plane. And after this two-step misalignment correction method, we see that the epicardium is quite perfectly aligning with the epicardium in the long axis plane, as well as the endocardium also. However, even after this two step, if we see the same 3D sparse representation, we see that the contours are still not well resolved. And that happens because these two initial steps just performs the misalignment correction based only on the in-plane movement. That means here they try to optimize the consistency between the long axis and short axis slices by moving them along their original acquisition plane. However, in reality, this cannot happen because in reality, the patient can breathe or can move along any direction in the 3D plane. However, we cannot solve that based on these two steps. So in order to solve the problem, Here we have used a statistical shape model based method to optimally correct the misalignment between the slices. So we used a statistical shape model to solve this purpose. Now this shape model has been generated by a high resolution 3D cinema scans from 1093 subjects. Now the hearts were first registered to the template space, and then the principal component analysis method was applied. Now the first 100 principal components from the model can account for total 99.9% of the total shape variation. So this model can give us a good enough representation of the heart from these sparse slices. So what we essentially did is that we tried to fit this shape model to the sparse contours. What we did is that we tried to estimate the optimal values along the different principal axis planes. And we tried to minimize the distance between these contours, that means the endocardial and the epicardial contours, to the corresponding surfaces. And here the green surface is the LV endocardial surface, red one is LV epicardial surface, and the blue one is the RV endocardial surface. So we tried to optimize the consistency between the model and the contour so that the distance between the contours and surface is minimized. Now, after this shape, we get an approximate representation of the heart mesh. And then we try to optimally align these contours to this heart surface, but this time considering any outer plane movements also. Now, since we have this approximate representation of the heart now, so we can perform the contours to surface minimization this time as compared to the previous point-to-point minimization, which we did during the intensity based and contours by misalignment correction. And by that, we can solve the problem and provide an optimal misalignment correction from these contours. Now, please remember that this step, that is the fitting of the shape model and the final misalignment correction, can be solved even if we only have the short axis slices, because we all know that in many of the cinema studies, they only capture only the short axis slices, but not the long axis slices. And in that case, the previous two steps cannot be used because they are performed based on the consistency between the long and short axis slices, while this method can even perform when only short axis slices are present. Now, this is actually one of the montage of the 10 reconstructed 10 cases after our contour based and statistical shape model based method, and to show that how the method works. Now, if we just look closely into just one specific case, we see that initially the distance between the short axis and the long axis contours was very far and they were not very consistent. But after our optimal misalignment correction, we have been able to solve the problem quite significantly. And now the contours from the short axis and the long axis slices are quite similar and they are quite well resolved. Now, these contours are now very much well applicable for the attractor based minimization for the generation of the final 3D biventricular meshes, and we have used that and got our final biventricular meshes. Now, if you see the qualitative result, here we have generated the final meshes from the uncorrected contours, and then after the contours based misalignment correction, and then also after the statistical shape model based misalignment correction. And we see that even after the contours based misalignment correction, in this area, they are not very well resolved, because you see the distances between the contours and the surface were very high, while our new method have been able to well resolve the problems and have been able to minimize the distance between the contours to the surface. Here we actually have shown the distance of the contours to the surface using an error bar, which we have shown in the right hand side. Here also our method has been able to well resolve the issue. This is another example where our method has also been able to well resolve the inconsistency between the contours and the final reconstructed meshes. Now, this is the quantitative results where we have shown the result over all of our 10 subjects. And you see that our method have been able to consistently perform best as compared to all other methods. Except in the case of subject 3 and the subject 14, our method's performance is actually similar with the contour space method. But even in those two cases, our method provides less variation as compared to the contour space method. And in every other case, our method's performance is much better. Now, if we just combine all the results and see only for the three surfaces, epicardium and both endocardium, we see that our method performs statistically significantly better as compared to all the methods, and specifically from the contour space method. So to conclude, We have developed a completely automated method for misalignment correction for accurate modeling of the biventricular heart meshes, which can account for both in-plane and out-of-plane misalignments, and it is applicable even when the presence of only short axis slices along with both long and short axis slices. We have evaluated our method on a cohort of 20 subjects randomly selected from the UK biobank study, and we have been able to reduce the misalignment from 1.14 millimeter to average 0.72 millimeter. So with this, I conclude my presentation. Thank you very much for listening. Please feel free to ask any question now or over any of the provided contact links. Thank you very much.